Hello everyone, this is Xulong Tang from University of Pittsburgh. Today I'm going to present our collaboration work, Mix and Match, Reorganizing Tasks for Enhancing the Data Locality. Before going to the detail, let me first give an executive summary of our work. While minimizing cache misses benefits application performance, data movements in many core platforms or many core systems also plays an important role in shaping the overall application execution performance. However, for many task-based programs, task parallelism rarely takes optimizing data locality and data movement simultaneously into account. This is because of several constraints. For example, the task granularity is too coarse, the task is too complex such that the data locality cannot be achieved across the tasks. And also the task placement uses the task granularity to the coarse, which diminishes the opportunity one can obtain to reduce the data movement. And also the task scheduling focus on load balancing to ensure the parallelism, which actually diminishes the potential of data locality and reducing data movement. So in this paper, we propose a software approach that reorganizes the task in a data locality aware and data movement aware fashion. So our approach consists of two major contributions and four complementary steps. The first step is basically task partitioning into subtasks. What we did is basically we break the task granularity and partition it into a finer granularity, which we call it subtasks. And the second step in our approach is basically to generate new tasks using the subtask we generated from the first step. And this new task generation is based on the reuse and also the data movement. The third step is basically data movement aware task to core placement to reduce the data movements across the cores. And the last step is basically data reuse aware subtask scheduling to maximize the data locality within the newly generated tasks and also across the newly generated tasks. Experimental results using 10 multi-threaded programs shows that our approach improves on average 23.4 performance compared to the baseline. And also it outperforms two state-of-the-art data access optimizations for all the 10 benchmark programs we tested. So here is basically the outline of today's talk. First, I will give a background of the targeted many core architecture and also the task-centric programs. And then I will discuss our approach. I will start with a high level and also use an example to go through the four complementary steps in our approach. And then we will show the evaluation results, the performance and the execution time improvements. And finally, we will give the conclusion. So come to the background. First, let's see the typical high-level view of the many core systems. So in this paper, we target Xeon Phi type of many core coprocessors. So in these systems, the cores are connected through a scalable on-chip network. And in this example, it basically uses a mesh as an on-chip network. And each node in this network consists of the cores, the private L1 and L2 caches, and the L2 cache is maintained to be coherent using the directory-based cache coherence. And also the data movement in this system really depends on the requesting node or requesting core and the data location. And in this paper, we also target the task-centric parallelism. So essentially, the task-centric parallelism are basically multi-threaded or multi-programmed applications. For example, in an OpenMP implementation, we can treat each loop iteration as one task in the parallelization. Other types of task-centric parallelism include the Intel thread building blocks, the Silk plus, etc. And the problem actually in this task-centric parallelism or programs is that the tasks are not written to be aware of the data locality and data movement. Well, one can Intuitively thinking, we can use a classical or traditional data locality optimization and data movement optimizations at the granularity of the tasks. But in reality, due to the task complexity and the coarse task granularity, those optimizations rarely achieve a promising improvement. Actually, in our paper, we started, if we just apply the traditional optimizations on the task granularity, it yields a very marginal performance improvement due to the cost granularity of the original tasks. And to target this problem, in this paper, we propose a compiler approach called mix and match. And our approach basically reorganizes, reshuffles, and reschedules the tasks in a data locality aware and data movement aware fashion. Our target is basically to achieve both the intra and the inter-task data access optimizations from the data locality perspective, as well as the data movement perspective. So come to our approach. First, let me give you a very high-level overview of the proposed mix and match. So in this figure, the top part, the figure A, shows the original tasks. Let's assume we have 4 tasks to start with. And the circle within each task basically represent or indicates the subtasks. And the purple line actually connects the subtasks to indicate the data reuse between the subtasks. As you can see that in the original task organization, there can happen there are reuses or data sharing across the boundary of the original task. For example, T11 has a data reuse with T21, but T11 reside in task 1 and T21 reside in task 2. So in this case, if one wants to really achieve the data locality across these 2 subtasks, we need to schedule the task 1 and task 2 both close in time during execution, as well as close in location when we map them to the course. For example, we want to map them to the neighboring course. However, because the granularity is coarse for task 1, task 2, such mapping may not yield good performance gains. For example, it may contradict with a potential load balancing. It may hurt other data locality opportunities or potentials, and so forth. And the bottom in this figure, basically the figure B here, shows the newly generated task after applying our mix and match approach. As you can see, we basically reorganize the subtasks and generate new tasks such that the intra-task data reuse for the new tasks basically maximized. So giving the particular example here, T11 has a reuse with T21, and now T11 and T21 are basically residing in the same new task, which is labeled as new task 1 here. So to achieve such kind of subtask reorganization and grouping, our approach basically have several key steps. The first step is basically initial code analysis. So in this step, we take the subtask granularity specified by the programmer, and then we generate the dependency graph to the subtask granularity. And the second step is basically we construct the subtask graph. The subtask graph basically captures the reuse intensity among the subtasks. So this graph is basically a weighted graph. And the third step is subtask clustering. So in this step, we're basically regenerating the new task by clustering the subtasks with the goal to maximize the intra-task data locality and minimize the intra-task data movements. And the next step is the new task to core mapping. So in this step, we're trying to map the newly generated task to the course such that it is close to the data location and also maintain the load balancing. And the last step in our approach is subtask scheduling. Basically, we're shuffling the execution order of the independent subtasks within the newly generated tasks to minimize the inter-task data movements. So let's actually visit each step individually and use an example to show how our approach works. So the first step is basically constructing subtask graphs. So in this step, we basically break the original task granularity based on the programmer provided subtask granularity. And it is to be noted that different subtask granularities is basically striking a trade-off between optimization benefits one can obtain and the compiler complexity. In our current paper, we assume the subtask consists of a single program statement. However, this is parameterized in the framework and can be specified by the programmer. And we also show with different size of the subtasks, the yield performance also changes. And in this step, it also generates two graphs. The first graph is basically called subtask graph to capture the data reuse intensity among the subtasks. And the second graph is the dependency graph at the subtask granularity, which basically provides the constraint while we do clustering and scheduling, we need to follow the dependencies across the subtasks. And let's use an example to illustrate this step. So suppose that we have three tasks, F, G, and H. And let's also assume that the subtask granularity is 4 statements for illustration purpose. As a result, each of the original tasks consists of 2 subtasks labeled as F1, F2, G1, G2, H1, and H2. And now, based on these subtasks, we first generate a subtask graph. It is a weighted graph with a weight on the edge to indicate the intensity of data sharing across the subtasks. For example, between F1 and G2, the weight on the edge is 6. It basically means that there are 6 data reuses between F1 and G2. And if we observe from the code, we can see that the variables A, B, C, D, F, and E are basically shared across F1 and G2. And simultaneously, our approach at this step also generates a dependency graph at the subtask granularity. So in this example, the dependency, there is one dependency arrow between the F1 and F2. This is because the F2 and F3 generated in F1 subtask is being used by the F2 subtask. And the next step is basically subtask clustering. So in this step, our goal is basically to generate new tasks that are eventually mapped to the course. And for those new tasks, we want intra-task data reuse to be maximized and inter-task data reuse to be minimized, which basically means that the potential inter-task data movement is minimized. So to achieve that, we apply a very classical algorithm, the KR algorithm on the subtask graph, basically the reuse intensity graph. And we also follow the dependency graph, make sure the correctness of the execution, and when necessary, we insert synchronization primitives. And using the same example, after applying the KR algorithm, we will basically have a graph showing here. And this graph basically indicates that F1 G2 should be clustered or should be regrouped to one new task. Same for G1 H2 and H1 F2. And remember that there is a synchronization to be inserted between the F1 and F2 because of dependency. And come to the next step is basically a new task to call mapping. So in this step, we basically tries to map the new task to the course that are close to the data location such that the potential data movement is reduced. And the same example, using the same example here, suppose that for F1 and G2, most of the data request comes from the memory controller on the top left corner. We're basically trying to map this new task to the core that close to that memory controller. But note that since our approach is compiler guided and compiler based, it is not guaranteed to achieve the optimal data movement when we do this new task to call mapping, because during execution, the data might be cached and served from other places based on the coherence protocol. And the last step we do is basically subtask scheduling. So in this step, we basically try to reorganize or change the order of independent subtasks to capture the potential data reuse among the new generated tasks. For example, in this figure, the blue line basically represents the newly generated tasks. For example, F1, G2 are the first task, G1, H2 are the second, H1 and F2 are the third. And it is to be noted that there is also a significant reuse between G1 and G2, which is highlighted using the red color here. And if we want to capture this data reuse, we basically want to execute G1 and G2 close in the space and also close in the time. So for that purpose, what we do is basically we reorder the execution order of F1 and G2 in the first task, such that G1 and G2 now are executing closing time. And remember that the synchronization primitive is inserted in the third newly generated task because there is a dependency between F1 and F2. So those are basically the 4 complementary steps of our approach. So come to evaluation, we implement our approach using the LLVM framework, and we evaluate the mix and match on Intel Xeon 5 coprocessor with a cache mode and sub-NUMA cluster mode. And we use 10 multi-threaded program to test our proposal and also compare it with 2 state-of-the-art approaches. So come to the main results. In this figure, we show stepwise improvement by applying each step in the mix and match. As you can observe from the figure, each of the subtask clustering, subtask placement, and subtask scheduling is crucial for the success of mix and match. And they basically brought the execution time reduction with 10.1%, 6.9%, and 6.2% respectively. And to further understand where this performance gain comes from, we first perform a study of the CDF distribution of the Manhattan distance. And using this distribution, we can see that mix and match effectively reduce the data movement, basically the number of links involved in the data accesses. And also, we show the L2 misread reduction and the row buffer misread reduction. And this reduction comes from the data locality aware the new task generation and scheduling. And as we can observe from the figure, our approach achieves 29.2% and 13.8% misread reduction for L2 and the row buffer respectively. So for more results and discussion, they are present in the paper, including comparison with 2 state-of-the-art approaches, employing different subtask granularities, and so forth. Come to conclusion, optimizing data locality and data movement in task-centric applications on many cloud platforms can significantly improve the execution performance. Original task organizations in task-centric programs are agnostic to such opportunities due to task granularity and complexity. So in this paper, we propose a compiler approach that reorganizes, reshuffles, and reschedules the tasks such that both inter and intra-core data locality and data movement are optimized. Experimental results shows that our approach effectively reduces the L2 misread, the row buffer misread, and also the data movement, and it yield 23.4 performance improvements. So that's all for today's discussion, and thank you for your attention, and I will be happy to take any questions. Thank you.